Okay.
We also have bathtubs with mattresses and
Okay, so somebody who took this class before, actually it's the other tutor, it's Autumn Mills, pointed out to me, she's like, the way this class is built is we are kind of like looking at the little pieces that make up weather, and then we're we're going to get to the severe weather, but we kind of need to understand. One of the things we need to understand is this idea of wind, okay? And so today I want to kind of get you thinking about wind, which there's a little bit of wind. It's a little bit gusty, okay, from the south, almost kind of southeast almost. Yeah. So the thing, in order to talk about wind, we need to revisit air pressure. So one of the things you guys told me is you climb a mountain, the air gets thinner, and that's kind of what we're seeing here. You climb a mountain, the air gets thinner, okay? And think of those gas particles as creating a pressure on anything they come in contact with, okay? So that's kind of what we call the, let's see, what would it be? The vertical kind of, the way air pressure is vertically speaking.
Yeah.
So I brought this little piece of green right here. This is a 1 inch by 1 inch, okay? Now, when you go to put air in your tires, you probably put it in according to PSI, pounds per square inch. Okay, cool. That's like, I think my mom's tire is like 30. Is it like, does that sound right for a tire? Okay,
Mine's
good.
34.
34 pounds per square inch. So, okay, so that's my inch square inch. Okay. So basically, when we're walking around, just the air runs about almost 15 pounds per square inch, 15 psi. Okay, so we can kind of think of it in terms of basically kind of all those gas particles hitting something there, 15 psi. Also, we can kind of think of it as basically if you were to take that, it's kind of neat to take that area and go up to the edge of the atmosphere, take that chunk, okay, it would weigh about 14.7 pounds. About 14.7 pounds.
The whole chunk from like the ground on up to the top of the
Yep. This area. They weigh about 15 pounds. And so what I did was to go in, now it's not metric, but it's, sorry, of course, pounds is English, but this is, I'm going to pass this around. Oh, this is like the weight of a column of air. Going from the top of the atmosphere down. So when you say gas doesn't weigh anything, what does?
Heavy?
I don't know.
Oh, it is heavy. Oh. Okay.
It wasn't the best idea.
So pounds per square inch is basically gas pressure. Okay. Yeah, there's no.
You like aerobics?
Try some extensions.
I need to work out a little bit.
So air pressure is important in understanding what the weather is and what it could do. Air pressure. Okay. So instead of pounds per square inch, in weather we talk about other units. If you guys have been reporting the pressure on your weather journals, you probably have reported it in units of inches. I'm going to talk about what that inches means here in a minute. But that inches that you've been reporting, okay, 13 or 14.7 pounds per square inch that's about sea level pressure. Is equal to 29.92 inches. Okay. These other two, the atmospheres, we use that a lot in chemistry. We talk about atmospheres of gas pressure. This one up here, the 1013 millibars, that actually is an important unit in weather maps. The MB you see a lot on weather maps.
I'm not alone.
It is heavy.
That means water.
You could just leave it. I will not be able to pick it.
Okay. Yeah, I'll come get it. You can indirectly know how heavy it is. So if you want to, next to the MB or millibars, put weather maps, you can. Okay. Inches of mercury is kind of what we see on the internet.
How many pounds is the black one?
What's that?
Your black weight?
It's 14.7.
Each one of these weighs a kilogram.
Which is
I looked it up. I Googled so these collectively are about 14.7 pounds.
A piece?
Oh.
No, collectively.
Collectively?
Yeah.
Oh, wow.
That's
I
terrible.
know. According to to my
No,
calculation.
that I can't lift it.
Okay. So
It's different than if it was a dumbbell.
it is.
Concentrated dumbbells.
So one of the things about units, so here on the left we have inches. So this is actually, I'll say internet. So this is what you've been recording, your inches. Now one of the things I think is interesting is if you've been writing those down, you notice that actually it doesn't vary much. It doesn't appear to vary much. A little bit of change in inches is a big change in pressure. And pressure is very important for wind. Okay. And this other column over here is millibars. And so we kind of have some things kind of put in perspective. Typically, if you're at sea level, the pressure runs about 14.7 pounds per square inch. The pressure runs about 1,013.25 millibars, 29.92 inches. When we talk about hurricanes, in the center, the eye of the hurricane, which I bet you guys have heard about, the eye of the hurricane has, in order to kind of gauge how intense it is, they look at how low the low pressure is, the central low pressure. So we kind of have some indications there. These up here, these are like an H on a weather map. Those high pressures, generally high pressures bring you kind of dry conditions and kind of calmness, kind of dry and warm. Okay, so how do you measure pressure? Okay, so there is the messy way, a mercury barometer. I don't know if any of you guys have played with liquid mercury that came out of thermometers before. I have. It's really dangerous. It is bad. But, so don't do it now. But they didn't tell us that then. Okay. So this is messy, mercury barometer. Aneroid barometer is right here. This is the not messy one, an aneroid barometer. Anything aneroid means minus of air, subtraction of air. So I brought this one.
What was it?
Aneroid. Aneroid barometer. Yep.
That means no air.
No air, yeah.
Oh,
Anaerobic.
What's this thing called? Isn't this a pressure measure type thingy?
Could be. That would be kind of like, that's kind of like that's an easy.
I know, I saw it on my friend's wall and I was like, oh, this is a weather picture. I could take that.
Yeah. That kind of looks like a mercury barometer, a little bit like this. But it's not mercury, it's just liquid water. And so they're looking at the liquid, the movement of the liquid in the skinny part and the fat part to get a sense of what the pressure is.
Can I use that for one of my weather pictures? It's weather.
No. Tempting, I know. You said you had more than you need anyway.
Yeah, so I'm going to use it.
Okay. But it won't count towards your 10. But it will be nice in it. Thank you, good. We're both on the same page there.
No, I haven't even started.
So here's the messy one. One of the things about liquid, mercury is it's a liquid and it's relatively dense, which kind of makes it better than some fluids. So basically what you do in order to get a sense for the barometric pressure is you have, this is a tube that is closed at one end. So it's closed up there. Okay, you draw a vacuum, and I know this isn't how you do it, but I feel like you draw a vacuum, you stick your finger on the open end, this is open, stick your finger on the open end, and you dip it in the liquid mercury. Now, I know that's not really how you do it, but that's kind of how you do it, because you need a vacuum up there. So basically, this thing is kind of free-floating. This column of liquid mercury kind of free floats. Now, it will float, it will go up farther if there's more pressure here. And if the pressure, now what is this is like the pressure of the atmosphere. This is the pressure of the gas particles. Okay, that's what's in the open pan. As the pressure lessens, then actually the liquid in the liquid mercury in the column will go down. So when you guys have been reporting like 29.9 inches, you've been actually recording how far up the mercury was up in the column. So that's it. It's the messy one. Okay, this is the not messy one. And I'll go ahead and pass this one around. It's been through a few lectures. Okay, as it comes around, if you want to just watch me gently, which which needle is moving if I squeeze this?
The big one.
The big one, the black one. Yep. So actually, that's kind of, they're made to be kind of flexible like that. Okay. So it moves a little bit. Okay. I think I went around one time and it just kind of got. So I'm going to go ahead and send this around a little bit. When it comes around, be sure to kind of look at the scales. The scales are kind of fun. It's been what we've been talking about this morning. The inner scale says millibars, and it has centimeters, and has inches. 3 scales on there. Now, what this is, okay, this thing is movable. It's meant to be movable. And it tracks what we call tendency. Okay? So, I'll put all these up here. Do you remember a minute ago when I said highs? Those are kind of like boring, kind of like, well, actually not boring, they're wonderful days. I'll pass this around. So highs, generally, if you see an H on a weather map, kind of be thinking probably clear skies, warm temperatures, high pressures. If you see a low, not so much. So actually, as this comes across, over here high, over here to the right, okay, very dry. Okay. Our ancestors were pretty smart. Okay, low pressures are stormy. Okay, so L's will bring clouds, maybe precipitation. Highs will bring the opposite. The other thing is tendency, and this is what I was trying to get to with the little gold thing that moves. So one of the things I said, if you could get tendency on a weather log, that would be great. But if the barometric pressure is rising, okay, actually we're probably coming into some dry spells. If it's falling, we're coming into some, what?
What's the thing that tells you that there's going to be an earthquake?
Seismometer?
It's like a car.
Seismograph?
Seismograph? Seismometer. Seismograph.
Because I remember seeing it on Full House, and she drew a picture of it, and like on the wall.
That's kind of confusing.
Oh, she's asking about earthquakes and how to sense an earthquake.
Yeah.
So they have them on the walls? Oh my gosh.
Yeah.
Oh, my goodness. Yeah, if you can experience an earthquake, get a little bit of video of it, you can actually.
I get in danger.
Oh my
It was 20
goodness.
years ago, I didn't have a smartphone then.
Oh, okay, he's been through it, that's right. Oh.
Been through 3.
I've been through 2, but they were really small.
Earthquake?
Yeah, they were having problems in Oklahoma, and then I went through one when I was really little.
I call that a problem. So did you have on the wall, did you have a sensor thing that like they were talking about? Okay. That's neat though.
That would be scary if you're walking down the hall and you looked up and you're like, oh, there's going to be an earthquake today.
Yeah.
No. I
Not
would
good.
scream and cry.
The-
The
yeah.
earthquakes.
It's weird because the earthquake comes from below and the weather comes from like above, you know.
Is it true that you're supposed to stand by a doorway?
Yes.
Why?
Because the doorway is strong because of the way it's built. And the
What about a
walls
table?
can fall in.
Yeah.
Oh.
Could you get under a table if there was no doorway or
Yes,
table?
getting under a table is better than,
So I don't know if you heard this, but doorways and tables
What
if
about
you're
bathtubs?
experiencing an earthquake.
and if you're in a bedroom, pull your mattress off the bed and get under the mattress.
I don't think
I feel
bathtubs.
like that'd be squishy. You get squished.
Bathtubs.
It would be.
Springy though, so something falls on you.
Yeah, that was
That's true.
protecting me.
That's true. But I'd still feel like squished.
That's why I will never go to California.
So, the one last thing, did you guys all hear I said about the little gold pointer thing that's movable? So, like, what you do is you set it on what it is now, and then 24 hours later, or whatever, you come back and see where the black thing has moved. So, like, if it's moved over here, your tendency is to increase pressure. If it's pressure's rising, if it's moved over here, your pressure is falling. So that's kind of how that works. Okay. So we're going to see a weather map here in a minute, and the units are not going to be inches, this pressure, okay? But the units are going to be millibars, okay? So millibars is the preferred weather map pressures. So the thing is you guys know that if we go up in elevation, what should happen to the pressure?
Should drop.
Less, exactly. Pressure drops as you go up in elevation, exactly. So when we look at weather maps, though, they actually adjust. If you're looking at, like, weather maps, like we're going to be seeing some weather maps, they actually kind of compensate for, like, going up in elevation, having less pressure. Because they need to kind of compare apples with apples to remove the effect of elevation.
It is a fun game.
It's a type of what we call standardization. So, for instance, if you're at sea level, okay, this one's at sea level, this first station over here on the left. If you're at sea level, whatever your whatever your barometer says, okay, whatever pressure it says, that's what you go with. So 1,008, they report 1,008. Now, if you're up, in this case, we're up 1,200 meters above sea level. Well, we know the air is going to be thinner. We know that the pressure is going to be less. The barometer up there read 886 millibars. Now, if you go back to that sheet, that table of like low, crazy, scary low, that's kind of scary low for surface pressure. But it's low because of the elevation. So what they do actually is they tack on some more pressure. And I don't have a formula for this, but they tacked on 120 millibars, okay, before that. Okay. So actually on a weather map, you're going to see 1,006 millibars. The last one is up even higher, so notice they tack on 180 millibars pressure. Okay, so that's kind of how they correct it. It's corrected for elevation. So that's how that works. So speaking of weather maps, these might kind of look like the isotherms we talked about in Unit 1, okay? But they're called contour lines. These contour lines now are not connecting locations with the same temperature, they're connecting locations with the same pressure. They're called isobars. Okay, not isotherms, isobars, because it's the same pressure. Isobars, yep. As in barometric pressure.
Kind of look like the isotherms.
They do look very much like isotherms.
There's just
Exactly.
a bigger set of numbers that goes with them. So.
Exactly.
What's the red arrows?
The red arrows are kind of showing you kind of the from high to low. The red arrows are all from high to low. High, and actually that's important because on the, like 2 slides from now, see how I've gone from high to low? Mm-hmm. That actually is the direction that wind will go.
Okay.
So this little arrow right here is kind of wind. And it kind of makes sense. Check this out. If I were to kind of show a high, all these little dots are little gas particles. Okay, and then over here I'm going to show a low. Doesn't it almost seem like it's going to go from high to low? Mm-hmm. Yeah. So these isobars are all, I'm kind of thinking they're like every 4 millibars. So we have 1,012, 1,016, 1,020, 1,024. Okay. And one last thing before I leave this. If you find a low, it should be, does this make sense? If that's a low, when we're going to look at them here in a minute, we're kind of climbing out of a low. If we look at those ice bars, it's getting greater and greater pressure. So let's see if it is. It's hard to find, so let's see. I wish they labeled more of them. So 1,012, well, you just kind of have to take my word for it, I guess. So 1,008 is right here. 1,008. And this should be 1,004. And this should be 1,000. Kind of see what I'm doing there? Yeah. So then this one would be what? 996. Does that make sense? I should have labeled them.
Why? Is the 996? Would you remember?
Because I'm subtracting 4 millibars.
Oh.
If I did it right, yeah. I'm subtracting 4 millibars each time I go in. Yep.
I get it.
Yep.
I get it.
Yep. And so kind of, this one actually is marked stepping out. This is 1,012. Yep. I guess this one's a better example over here. Okay. So if you step out, you're at 1,000, you step out further. You're at 1,004, step out further, 1,008, step out further, 1,012. So it's kind of going up. Okay. Now this one, in meteorology, one of the things we need to talk about is kind of talk about, the last one we saw was surface pressure. Okay. but we need to be able to kind of talk about upper level pressure. We kind of call this a loft. What is the pressure aloft? Now, though these are not isobars, honestly, these are what we call iso heights. Don't blame me, I know. They're iso heights. They're elevation you need to go to. The contour lines are the elevation you need to go to in order to reach, in this case, 500 millibars of pressure. 500 MB. Now put that in perspective, what we just talked about. 500 MB, how many millibars is this down here? Remember?
1,006.
Close. 1,000, well, normal sea level millibar pressure. 1,000, not 8, 13. 1,013 millibars. So 500 millibars is kind of about, pressure-wise, kind of out here from here to outer space. But remember that it's more dense here and it's not linear. So, okay. This is just to kind of reinforce the idea of bless you, what happens when air gets squished. Okay, kind of from left to right, we kind of see air is getting squished. Two ways, many ways we can see air is getting compressed or squished. One is basically from left to right, we're adding, this is a movable kind of little piece of metal on top, movable piston. We're putting more weight on it, we're squishing it. The other thing is, can you kind of discern the color? It's kind of light blue here, a darker blue here, and the darkest blue here, where the dark blue means a lot of gas particles crammed close together. The other thing, remember that we talked about pressure gauges? What's the pressure gauge doing? From left to right.
Right.
Yeah, so those are all just kind of showing you. So which one would you say is at upper elevations, A, B, or C? I think A to me looks like it would be up here, yep. And C looks like it would be down here. So you kind of take this and kind of that. So that's kind of what we call the vertical, what's going on vertically. Okay, so again, vertically, we have nice and cozy gas, these are all gas particles, okay, they aren't connected, okay, but nice cozy gas particles, high pressure, 1,013 millibars, kind of typical sea level pressure, and then we have, as you go up, what happens to the pressure. So to kind of put that, that isobaric chart in mind, this would be kind of, remember we looked at kind of that other, yeah, that elevation. Okay. All right. I'm trying to decide, yeah, because I want to get to this one topic. Okay. So we have a difference in pressure. We have high pressure, low pressure. You guys would tell me that. Now, we have a difference in pressure. Remember a minute ago we had our lows and our highs. We have a different pressure, what we call horizontally. How do we get highs here and a low there? What's up with that? It's an important player in meteorology, but how do we get them? There are three ways you can get them. One is temperature. Okay, so I think I probably said, maybe even recently, if we have a drastic change in temperature from day to day, oftentimes that's associated with a crazy wind. Okay, differences in pressure is what creates wind. So if you have differences in temperatures, you have differences in pressures, so you have a crazy wind. So in general, if you think cold, think high pressure. If you think warm, think low pressure. And can you almost kind of see this high because they're close together and a low here? So that's kind of how that works. So that's going to be important. So we have a high pressure here. I can't see that very good. High pressure here and a low pressure here. Well, another way, and this is where it's almost, if you guys know what counterintuitive means, it means like it feels backwards. Well, this is almost a counterintuitive thing. If I were to ask, say, oh, it's a muggy day out there, what do you think about pressure? You'd probably say it's a muggy day, the pressure is high. Yeah, because it's hard to breathe when it's a muggy day, but that's for something different. If you have high humidity, actually that brings with it a lower pressure. Okay, so again, it's counterintuitive. And the reason I kind of listed why it has to do with the mass of a water molecule versus the mass of just regular nitrogen and oxygen. But what I need you to know is that if it's moist, it's a low. If it's dry, it's a high. Oh my gosh, that rhymes. Okay. Natalie looked up too, and she's like, right up your alley, right? And then the third way, you can at the surface get a difference in pressure. And it was one that we talked about, a lifting mechanism, okay? Because do you guys remember, said one way to get air to lift is to have kind of wind kind of meeting somewhere, okay? So that's a lifting mechanism. This is called convergence right here. This one is convergence. But do you also see where what convergence does is it creates a high pressure? And we could kind of do something similarly, and I think I said the whole candy in the schoolyard convergence. And then if somebody throws up because they ate too much candy, that creates what we call divergence. So here's the person threw up, right? Okay, everybody's leaving except the teacher. Okay, so that's diverging air. Okay, and with all that air leaving, that creates actually a low. Okay, so that's just another way that we can kind of have alternating highs and lows. Sorry.
I won't forget that one.
Okay. So finally, I brought some props, and this is kind of where I kind of wanted to get to today. So we have this idea of we have high pressure and a low pressure. And honestly, wind is basically the movement of air from a high to a low pressure. Air is moving from high to low. Okay, that's creating wind. That's it. That's it, in a nutshell. In a nutshell. So these kind of blue, purple lines these are isobars. That looks like a football field, doesn't it? Okay. So they're nice kind of straight isobars. We have a high pressure over here and a low pressure over here. So the arrows are showing you actually the direction that wind is going to move. And I brought some examples here. Okay. Start with the tame one. So actually, like if you squeeze a bulb like this, okay, it's kind of like, remember the other day I said, if you try to catch a feather and you go to get it, you basically, it scoots away from you, okay, because you're creating a high pressure. And so like when you squeeze this bulb, you're creating a high pressure, low pressure, and so the wind in here, or the air in here is going to relocate out. Okay, so that's that. So then the other thing, obviously, I brought in here is the whole balloon thing, okay? So right now, the pressure in this balloon is pretty low, okay? We can add gas particles, and it's going to increase the pressure in our balloon. Okay? So there's more pressure and more pressure. Now what happens if I go ahead and let this go?
It's gonna make a noise.
It's going to go that way, for action-reaction sort of thing. And why is it going to go that way?
Because the air is moving that way. It was actually blowing out this way.
The air is going to go this way, and it's going to go back that way. So the air is going to go from a high to a low pressure, right?
That way.
Yeah, exactly. Very good.
If it was a bigger balloon, there was less conflict.
Yeah. So I think.
Had a balloon this big pop in my face.
Well, that
My aunt owns
is a good
part
place.
of it.
That's as far as I wanted to get you guys. So very good. So we'll kind of take a running start at it and talk more about wind on Wednesday. Wind on Wednesday.
Doesn't feel very good.
What?
Does
Did not feel very good. Okay, so
So are
my
you gonna
aunt
come
literally
down and
works
get your
now for a living,
handouts?
and she comes to
If anybody else wants their handouts, I'm going to my office, but otherwise I'll just bring them Wednesday. I will
And
remember.
so one of the kids pulls the balloon, but it's completely silent, and the little kid helps try, and she goes, "We're having a party!" Ever since then, incredible balloon pops. That's what we say. Maybe. Hey. It's pretty funny.
Thank you.
Thank you.
My square inch.
You're wearing shorts.
67 degrees outside, girlfriend.
Still
You gotta get with that warm weather
How warm
feeling.
is it right now? Is it
67.
already?
Really?
Imagine if the sunburn.
Oh.
It's only like
I'm trying to
9
get some
o'clock.
sun on these legs. They're kind of
No,
tan,
that's-
but I want to get them
About
tanner.
noon.
Oh,
But-
yeah, it's clock's out. But still, I mean, that's pretty.
Yeah, I thought you looked tan already.
That's a good thing. It's gonna be even tanner when I get back. Got a new patio I can lay out on.
Nice.
New lounging chairs. A
You're gonna go
trampoline.
storm chasing?
When I get back. Actually,
Only if it's okay
if I'm
with your
driving
parents.
like down, if it's not in Oklahoma, if it's like in the bottom part of Missouri by Joplin, because I'm gonna be down by there. It's really bad tomorrow. Say a prayer for me.
Because why? The weather's bad down there?
It's getting ready to be really bad.
Well, I hope you're
The
wrong.
tornado risk is going to be worse down near like Louisiana area. No?
Tip of Missouri, part of Oklahoma,
Oh,
and then
what's
part
the
of
torque on?
Arkansas. That tri-state area right there, bad news.
What's the torque on?
Huh?
What's the tornado?
The percentage of a tornado happening there versus here is 85%.